Um, okay, how it feels. Okay, thanks for introducing. So I am Michał, and I will be talking about Cyclo, that is lightweight lattice-based folding via partial sum check. And this is a joint work with Albert, Helger, and Urmas. So, okay, it feels a bit weird. Okay, to start off, let's set up some background. So, what is folding scheme? Folding scheme, in a very high level, it is a protocol that takes a tuple of L relations in some language, some witness statement tuples, and turns it into a single relation. So we have some protocol, some folding scheme which takes L relations and produce some output relation that we call an accumulator. Actually, to be more precisely, we also want then to take this accumulator and also put it as an input for the next level of folding. So to be more precisely, we should say that the folding scheme is a protocol that turns tuple of relations and the accumulator and turns into a single output relation. And why are we doing that? We have multiple reasons. So maybe we want to build something which we called incrementally verifiable computations, when together with the folding statement, we want to fold also the whole verifier circuit and basically build constant size unbounded proof. Why not? We may have some generalization like proof carrying data, or we can also use it for snark preprocessing. So we have some gigantic statement that we don't want to apply our snark on it, but first we may want to fold it a little bit to reduce the size and then apply our snark. And what are the properties of the folding scheme that we care about? So, of course, it has to be correct. We care about completeness of the protocol. And also we have some security properties that are pretty standard in this world. So when we talk about soundness, we speak of the language of extractability. So that this time we look at the protocol from the other side, we look at the output relation, and now we have an algorithm that we call an extractor, which has a black box access to the prover and can potentially rewind the prover in such a way that it outputs the input relation. Crucially, and we will take advantage of that a lot in that presentation, the relation that we are extracting is not necessarily the same relation that we started from. It can have some differences, and we will focus on the differences a lot. On the top of that, we're having some standard efficiency measures. So we care about proof sizes, we care about verifier complexity, we care about prover complexity, like regular story. And actually, what is making a lot of lattice-based folding scheme common is some general framework of building lattice-based folding schemes. So we start from some meaningful language of relations. For example, this language can be R1CS. I will not talk what is R1CS, but just think that this is some language which is capturing some real-life relations. And then we are doing an operation that we think about this as a sum protocol, or more formally, we talk about reduction of knowledge. And this protocol is turning the relation into a linear relation, which is something we will mainly operate on. And this linear relation when we talk about folding schemes and all lattice-based snarks, it's typically like an I-type commitment. So we have some commitment key, and this commitment key lives over some finite field, but typically we think it of a cyclotomic rings, some polynomial ring with cyclotomic quotient. And then also on the bottom we have some constraints like some R times N, and those are the constraints which are the artifact from these linearizations. And then we have a witness, and in the lattice world we typically care that the witness is low norm. And now, since we talk about folding scheme, as I said at the beginning, we don't have one relation, but actually we have many relations. We have L many of them. So now if we have L many of them, and we want to apply this linearization step individually, it happens and that we end up with the relations which are slightly different. For example, that this M is the same, but this R, which is like an artifact of this linearization, is different. So we would like to do something to make them similar, to make the left-hand side the same, so that we can apply folding. So how do we do it? Here we are talking about. I want to introduce the sum check protocol. But the intuition is that we want to end up, we start with the tuple of L relations, and we want to perform some protocol that instead we will have one relation which has many columns, or so that the left-hand side is the same. So how do we do it? We take out this constraint that was first at the bottom, and we write it down as some vector matrix constraints. And now, instead, we think of it as a language of sum check. So with this tilde, we denote the multilinear extension. So that is a multilinear polynomial that evaluated at the points of the Boolean hypercube gives us exactly that vector. And we observe that upon aligning dimensions, this equation can be rewrote as this sum check claim. And now we can think that we don't have many, but again we have, for example, 2. But think of L many relations. And now we perform this sum check, or more precisely parallel sum check, with the same randomness, so that we end up in the evaluation claim, which is now crucially shares the same randomness here. And now, if this side can be inspected directly by the verifier, we end up that this point R here is exactly the same for all relations. And now, if we instead replace those random points R with the same point, we observe that those sides are the same. And now we can glue them together, and we are ready to perform folding. And folding is a protocol that the verifier samples some short challenge, and now the many columns of the right-hand side and many columns of the witness can be combined together via this random linear combination. Okay, but so I'm talking about this, but and this gives us the complete kind of idea of how to build lattice-based folding scheme. But okay, I gave this like a quite lengthy introduction, which is not even about our work, but it's more about how to set up the stage about the problems that we are encountering in the lattice-based folding. So the main problem is with norm growth. So we observe that due to this folding, we end up with due to these random linear combinations, we end up that the norm of the witness is gradually growing. And it's growing, and when we think about multiple rounds of folding, it will grow exponentially with the number of rounds. Similar thing, we call that notion of extractor. This extractor, although I don't define this algorithm yet, but it still extracts a witness which has some multiplicative factor. At the end, we have some problems, and those problems has been addressed many times in the literature, like we have Lattice Fold Plus, which also Salsa, Neo, which talks about those issues, but often those solutions end up to be quite heavy in the kind of communication or computation. And Cyclo provides one more strategy, which is more tailored for the usage of IVC, and it operates under the assumption that we considering a bounded number of folds in our composition. Okay, so to be more precise, we define the contributions of Cyclo. That is this partial range check, which is tailored for polybounded folding depth. We also talk about we also have an adaptation of Neo embedding, which allows us for translating the fields like R1CN's statements into the ring relations, which fits into the broader family of paper bits commitments. And also we have some analysis and heuristics about strong sampling set, which is this set that is used for folding. But in these presentations, I will focus only on the first part and only mention the other parts very shallowly. So partial range checks. Let's start with some some facts, which you should believe me are right. So first we stipulate that norm checks are inherently expensive. So also, and typically they get more expensive when the norm is larger. And also in application, we often have a strict requirements on this input relation, for example, of these R1CS relations. However, we cannot say the same about the accumulator. So the accumulator acts a bit specially. And Cyclo remedy to all of that issues is that we would like to perform a norm check only on the input parts of the folding scheme and simply let the accumulator norm grow. However, we design it in such a way that this norm is only additive instead of multiplicative. So let's inspect like the basic norm check protocol that was designed, that was introduced, but it's existing in the literature for a long time of lattice fold, not lattice fold plus. So we start from the witness, which lives over some cyclotomic rings, and what we would like to prove, we would like to look at the vectors of coefficients of that witness. So it's not like a vector of cyclotomic rings element or polynomial from polynomial rings, but instead the vector of coefficients when the n is the degree. And we want to show that the coefficients of that vector belongs to some lives in some interval minus b to b. And we observe that this holds if and only if the product over this range with the element minus index is equal 0. Of course, when the Q is prime. So let's try to think how this pi range can look like. For simplicity, we can assume that for soundness that Q is some super poly, like it. And what we are doing first, how to construct such a norm check. First, the verifier is sampling some polynomial, and now we are representing this claim as a sum check claim over all coefficients when this EQ is some separator polynomial which allows us to argue about each coefficient individually. And now we perform our friend, like our sum check polynomial, and we reduce it to the evaluation over a random point. And now the verifier claims the evaluation, prover claims the evaluation over this random point and sends it to the verifier. The verifier checks consistency. And now, to prove about this, it simply turns it into some extra constraint over our original relation. But okay, I presented it a bit shallowly, but the main observation which I would like to take a look is that in this polynomial we have a degree of this sum check relation that we are checking is linear with the norm. So if the norm is anything more than constant, it becomes just impractical. Okay, so what we would like to do, we would like to actually perform a range check only for the part of the input relation, and for now assume simply that over this input relation we have some control. So it brings more issues. Like we range check only this part, but we still didn't argue about this norm. Like, okay, if we range check only this input part, why does the norm of the both extraction and correctness does not grow aggressively? So let's take a look at the folding norm. So remember this image that now we wanted to perform folding. So what happens? We just take some random challenge, and then our protocol pi fold turns into some output relation. And now, if you think about this, then this challenge comes from some challenge distribution. But what we can say about this challenge distribution is that this is over some norm, but we would like to pay a particular attention to the first element. And actually, what we can do is that for folding, it is enough to sample all the coefficients except from the first one from some challenge distribution, but the first one can be simply set to 1. And this way, if we treat the accumulator as a first column, we start from some norm that we track separately, B0. And now, we observe that if in the other columns we have some very low norm, practically we can think of some constant, then the output is only again growing by some constant. So after performing one round of folding, we have the norm growth we have the norm growing only by some additive constant because of how carefully we are setting the challenges. And now we are thinking that if we executed this folding scheme many times, then the norm growth is only linear with the number of folds. Okay, so we talk a bit about correctness, but let's take a look about this more difficult part, that is the extraction process. So yeah, we have some algorithm, we have this extractor, and now we would like to design this extractor. So in this extractor, for each columns 1 to L, and I'm counting from 0, so excluding this one, we are using the same argument as we use typically, so using some coordinate-wise forking, rewinding, and we end up with some witness here, which is potentially of a larger norm. But then on those parts, we think ahead that here we actually we executed before this sub-protocol, this pi range that is arguing about the norm of this witness. And only after thinking about this, we look at the accumulator. So now, since we have this range argument on those parts, in the accumulator, we can simply take a look at any accepting transcript and observe that if we have norm of our output, if you have our output witness, and we have witnesses for all of the columns except the first one, then we can simply extract the first one by doing some algebraic like addition and multiplication. So, and from this, we again take a look at the norm. So we start with this witness of the output norm beta out. And now we observe that this extract norm is again growing by only by the additive factor, so the number of columns, then the norm that was explicitly ranged times some expansion factor of this challenge set. So now again we observe that if we have too many rounds, the norm of the accumulator grows only linearly with the number of rounds. So putting it all together, we start from accumulator of some low norm. After t rounds, it grows only by some linear factor in t, and then in the extraction we get also only linear impact. So we observe that the impact is only in both correctness and extraction is only linear. So now this is the main contribution of Cyclo. So now let's answer to this question that probably you are thinking that, okay, what if our witness is initially not very short? Here we are giving one more protocol that is maybe okay. So what if the witness is not short? Like the typical solution that you can come across in the literature, that we simply want to take a witness, apply some decomposition so that we end up in the multiple columns of the witness and the multiple, but then we need to also have a multiple column. We need to send commitments separately to that column, and this is pretty communication heavy. The Cyclo proposes a bit different solution. Like instead of performing this decomposition and stacking the columns horizontally, we want to instead take this witness, perform an extension, which we called just to separate it from the composition. We want to instead decompose it and stack the decomposed witness together, and then commit it under a different commitment key. And when G is this decomposition gadget. And now we have only one column to be sent, and further, instead of we need to argue about the consistency of this extension. So we stack this matrix at the bottom, and with this composition gadget, perform some random linear combination, and this simply becomes again one more constraint in our system. So we put everything together, and for the same parameter set that is observed in Lattice Fold Plus, that we view as a state of the art of lattice folding, we observe that we get around 3 times improvement in the proof size, and we also did some estimates of the heavy parts of this protocol, that is computing this extension commitment versus computing the double commitment of Lattice Fold Plus, and we also have some 3 to 4 times improvements for the concrete parameters selected in the Lattice Fold Plus paper. And okay, I also want to give some short overview of some limitations of our approach, like when to use it, but also where not. So if you remember from the previous slides, the accumulator has now kind of special role. That is that we need to make sure that this is preserved from being combined with some random challenges, so we can get this additive growth in the norm. It is okay for the incrementally verifiable computation style, when we can always think about this accumulator just accumulating the new batch of our computation. So yes, so we have this accumulator, and then we want to perform some range checks on this input relation. So we get new accumulator, and we repeat that process again and again. And now in the extraction, we can have this argument. However, what if we don't have this case? What if, for example, we have some computation which requires some branching, some merging? We have some branches of computation which has to be like joined together. Then it may happen that we have, for example, 2 accumulators, if you think about more proof-carrying data context. And then we have an issue, because here we need to combine it with some challenge, and in the extraction we get some growth. Yeah, sorry. And we envision that the bounded fold, that in this case the Cyclo accumulator can be connected with different protocol, for example, with Lattice Fold Plus. And that's almost it. I just want to highlight the 2 other things in our protocol. So as I said, we also have this translation of field constraints into ring constraints, which I don't want to talk about. They are quite similar to those from NEOM. And also we have this characterization of this new strong sampling set, which allows us for using cyclotomic rings which are almost splitting, which is also transferable in the other context except of Cyclo. And that's it. I presented this was Cyclo, which contains of 3 parts. That is this partial range check, translation of this field-based constraints into ring constraints, and new approximate strong sampling set.
Okay, thank you very much, Michał, for this nice talk. I think we have like time for a very short question while the next speaker comes to the front. No question. So maybe let me ask you, how far do you think, like how much better do you think your techniques can get, like concretely, or you think this is like this route is?
No, I think here this is. I don't want to think about this technique as a general technique, but more as like a specialization into the case when we like think of this of a situation that we have like a very short input relations, and I think when it comes to general techniques, it's not very comparable. So I think the strength lives also in the composition with other protocols.
Okay, thank you very much. David, if you want to come.
Yes. So I